Swayam Prabha. Digital India. Educated India.
Today I will be talking on steel making fundamentals. Steel making fundamentals. Now, what is steel making in fact? Steel making involves removal of impurities through oxidation and slag formation such that total iron content of slag and oxygen content of molten steel at turn down are minimum. So, essentially steel making involves the turn down contents of iron in slag and oxygen in steel should be minimum. So, the fundamental comprises of slag formation, and oxidation of impurities. Slag formation, or you can also call it as a slag making or whatever, it is all the same. So, what is a slag in fact? Slag is a generic name, and in steel making it means that it is a homogeneous liquid solution of oxides, sulfides, nitrides, but mostly slags in steel making contains oxides and sulfides. When the slag is cooled and in the solid state, it consists of multi-crystalline phases. So, that is what in fact slag means. Now, say why does it form? Say why does it form a separate phase? The reason is very simple. For your information, all the oxides, for example, FeO, SiO2, MnO, Al2O3, MnS, which constitute the components of the slag, their density is in between say 3 to 5 or 5.5, whereas molten steel has a density of 7 or 7.5. So, liquid slag is lighter than molten steel, and hence it floats on the surface of the molten steel. This is number one reason why it forms a separate phase. Say number one reason is density. The density of slag is smaller than density of liquid steel, and second reason is that the oxides are immiscible in molten steel. So, second reason is immiscibility. So, density and immiscibility make the slag to appear as a separate phase in presence of liquid steel. Now, another question comes, say how does it form? How does it form? Say in steel making, what is done? Hot metal contains carbon, silicon, manganese, phosphorus and iron, and as oxygen is blown, then silicon is converted to SiO2, phosphorus is converted to P2O5, manganese is converted to MnO, and some of the iron is oxidized to FeO. So, because the steel making involves oxidation of impurities, and except carbon all the impurities forms oxides, and these oxides have density lower than molten steel. So, it will float on the surface of molten metal during refining of hot metal to steel. So, it forms essentially because we want to remove the impurities from hot metal and to get molten steel. So, that is how it forms. Now, say what is the role of slag in steel making? What is the role of slag in steel making? In fact, I will say this way, that make a slag and slag will make your steel. That is what the role of slag in steel making. If an operator does not know how to make a slag, he cannot make steel at all. So, the role of slag in steel making can be said in just one sentence: make a slag and slag will make your steel. So, that is what the importance of slag. But besides this, there are several other importance of slag in steel making. First, slag acts as a thermal barrier. As a thermal barrier, what does it mean? Molten steel is covered by slag, and slag is a poor conductor of heat. Hence, it helps to restore, or rather it helps to keep the heat within the molten bath, and hence heat losses are minimum, and therefore, we can call it acts as a thermal barrier. Second, it protects steel. It protects steel against reoxidation. Against reoxidation. Now, imagine a molten steel is uncovered and put in the atmosphere, then the iron oxidizes. Slag also protects steel against reoxidation. Third, slag prevents passage of nitrogen and oxygen from the gaseous phase to the molten bath, because there is a slag cover, and whenever the gas, for example nitrogen or oxygen from the atmosphere, can be transferred only through the slag, and in that way slag prevents the passage of nitrogen and oxygen in the molten bath. Fourth, it acts as a sink for impurities. That means, when silicon gets oxidized as SiO2, Mn gets oxidized as MnO, phosphorus gets oxidized as P2O5, then they form a slag, and by creating suitable properties in the slag, it acts as a sink for all these impurities which are coming from the oxidation of the hot metal. Fifth, slag also controls oxidation and reduction potential of slag. Oxidation and reduction potential. Essentially, it is the FeO content which decides whether the slag is oxidizing or reducing in nature. Relatively higher amount of FeO in the slag is called oxidizing, lower amount of FeO in slag, that is a reducing slag. Typical example, blast furnace slags have 1% or even to that order of magnitude FeO, so they are called as a reducing slag, whereas all steel making slags they have around 15 to 16% of FeO, so we can call them as a oxidizing slag. So, for the above purpose, the slag must contain certain physical properties And among physical properties, viscosity, melting point and density are important. Among chemical properties, basicity, oxidation reduction potential of slag, oxidation reduction potential of slag, and activity of component of slag, and activity of component of each of slag. Now, these above properties are determined by structure of slag. Above properties are determined by structure of slag. Now, slag in steel making, they consist of acidic oxides, basic oxides and neutral oxides. For example, SiO2, P2O5 they are acidic, CaO, MgO, FeO, MnO they are basic, neutral Al2O3, that means Al2O3 acts as base in the acid medium and acidic in a basic medium. So, let us consider the structure of pure oxides. Some essential features. Oxides have cations and anions. Now, one say metallic cations are surrounded by anions. If I have calcium oxide, then Ca2 plus ions and O2 minus ions. Ca2 plus ions are cations and O2 minus ions are the anions. Second important feature, cations of greater radius, for example, Ca2 plus, Mg2 plus, in oxides have octahedral structure. Whereas cations of smaller radius, say Si4 plus, P5 plus, in oxide have tetrahedral structure, For example, if you take SiO2, in the SiO2 each silicon atom is surrounded by 4 oxygen ions and each oxygen ions is surrounded by silicon. For example, if I take this is the silicon, it is surrounded by 4 oxygen ions and each oxygen is surrounded by 2 silicon atoms. So, this structure repeats in 3-dimensional and gives us the oxide like SiO2, which is electrically neutral. Now, another important feature is that in the acid slag, the tetrahedral network which is present in 3 dimension, they are joined at the vertex. Now, with that I mean, for example, if this is the one tetrahedra, of silicon oxygen tetrahedra. That is here oxygen, 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 silicon and here is oxygen. Now, the two tetrahedrons, they are joined at the vertex. For example, if I take this one, this. So, these are the two tetrahedra, they are joined at the vertex. So, this is one oxygen, another oxygen, another oxygen, 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 silicon, silicon and surrounded by the oxygen. So, these are the two tetrahedra. So, what is being said here is that because cations in acidic oxides, they have lower radius and hence they follow the tetrahedral structure. That means, each tetrahedron is joined at the vertex and this particular structure is repeated in 3 dimensional and hence we get the electroneutral SiO2. So, a 3 dimensional network will look something of this way. I will try to draw for you. So, this is a hexagonal network it forms. These are all the tetrahedron, they are joined at the vertex and so I am just showing the position of the ions. So, this is one oxygen, another oxygen, 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 oxygen. This is one silicon, this silicon, this is silicon, this is silicon and this is silicon and another oxygen is over here, over here, over here, over here and over here and say now in 3 dimensional this will go further this way. Further will be joined by another vertex. So, this is how in a 3 dimensional network a silica structure looks like this. So, what we can imagine at the melting point the same type of structure prevails. Now, as it is known, that means viscosity is inversely proportional to fluidity. Lower fluidity, higher viscosity, higher fluidity, lower viscosity. And fluidity is directly linked with the movement of the ions that are present in the liquid. So, if the size of the ion is larger, then you require higher force. If the size of the ions are smaller, then you require the smaller force. That means, if the size of the ions which constitute the liquid is larger, then the viscosity will be very high and opposite is true, that is when the ions are smaller, then the viscosity will be very low. So, the SiO2 just at the melting point, it will consist of very large size of combination of cations and anions and hence the viscosity of SiO2 just at the melting point is very, very high. Now, if we want to reduce the viscosity, then one option we have, what we do, we go at a very high temperature. So, at very high temperature what will happen, due to thermal dissociation the bonds will be broken and we have ultimately at very high temperature a mixture which contains Si4 plus and SiO4 4 minus. Now, we have reduced the size of the ions, hence the viscosity will decrease and fluidity will increase, but this requires a very high temperature and such a high temperature is not possible in case of steel making. So, now what to be done? Now, we also understand that acid oxides, in fact these acid oxides can also be considered as oxygen deficit. Because they are oxygen deficit, so they have a tendency to form a simple ions as the so called SiO4 4 minus. So, remember acidic oxides, they are oxygen deficits, that means they require additional ions to form a complex ions. You will understand better when I say basic oxides. They are oxygen donors. For example, if I take calcium oxide, it will give me Ca2 plus and O2 minus. So, Ca2 plus does not form that complex as silicon O4 4 minus. So, basic oxides are oxygen donors, and these O2 minus ions, they can move freely into the melt. So, now what we can do, if we want to reduce the viscosity of acidic oxides, that is only possible when we break all the 4 vertex of the tetrahedra. Then the size of the ion will be smaller, energy required for the flow will be smaller, and the fluidity of the slag will be very high. So, considering that most important oxides in steel making, they are SiO2 and Al2O3. Al2O3 also behaves in a similar way. Now, let us consider an addition of calcium oxide. So, if we add calcium oxide, what calcium oxide does? So, if we add calcium oxide, then calcium oxide dissociates to Ca2 plus plus O2 minus. Now, you see, if I supply 2 O2 minus, then I can break all the 4 tetrahedron, because the 4 vertex are joined by another 4 vertex. So, if I break all the 4 vertex, then I will get the ionic species which consists of SiO4 4 minus, and this is only possible when I add 2 O2 minus ions. Other way round, if I add 1 mole of calcium oxide, I am adding 1 mole of O2 minus ions. Now, this 1 mole of O2 minus ions will break 2 vertex. If I add 2 O2 minus, then it will break all the 4 vertex. So, if I make it, for example, if I put it, say total oxygen atom, say oxygen atom upon silicon atoms in SiO2, that is 2:1. If that is the case, then all the corners of tetrahedra are shared, all the tetrahedron, all the vertex of tetrahedron in a 3 dimension will be shared. The size of the ion which will be available, it is very high, and hence viscosity of slag is very high. Now, what I do? I know the basic, that if I add 1 CaO, I am putting 2 O2, I am putting 1 O2 minus ions, and 1 O2 minus ions can break 2 vertex of the tetrahedron. So, what I do? Now, I add, for example, 2 CaO, and 2 CaO will give me 2 Ca2 plus plus 2 O2 minus. That means, now if I have this oxygen atom upon silicon atom ratio, that is equal to 4:1, 4:1, that means the composition will be 2 MO into SiO2 or 2 CaO SiO2. In that case, what will happen? All links are broken, and the ionic species which will be available after the addition of 2 moles of calcium oxide or 2 moles of any basic oxide, then I will have an entity in the slag which is SiO4 4 minus, and size of this entity is very small, and therefore, the viscosity of the slag decreases drastically. So, that is what from the structural point of view, the addition of calcium oxide it rather decreases the viscosity of slag. Now, between the ratio 2:1 and 4:1, for example, you have the ratio 5/2 or 3:3:1 or 7:2. Say we add say here 1 mole of calcium oxide, we add 1.5 moles of calcium oxide, 1.75 moles of calcium oxide. So, in that order, as you increase the amount of CaO till you come to the ratio 4:1, the viscosity will decrease and attain a minimum value at the ratio 4:1. So, having understood the addition of calcium oxide on the structure of slag, now we can say that the progressive addition of calcium oxide till the formation of 2MoSiO2, there will be decrease in the viscosity of the slag. So, if we want to summarize, we can say that increase in CaO decrease viscosity of slag. Increase in temperature, no doubt it also decreases viscosity of the slag. Now, also Na2O or CaF2 decrease the viscosity of the slag to a larger extent as compared to when calcium oxide is added. Essentially, it is because the CaO and Ca2 plus, it has two charges. So, it will join 2 SiO4 4 minus ions. Na2O has single charge, that is 2 Na plus, and it will be able to join only 1 SiO4 4 minus. Similar is the calcium fluoride. In the calcium fluoride, F is also a 1 charge and it will replace oxygen, or it may replace all the 4 oxygen, and ultimately we may end up with the SiF4 only. So, that is the reason why Na2O and F and calcium fluoride, it decreases the viscosity at a drastically. Now, as regards the role of alumina, now alumina also behaves in the similar way, but alumina has a silica equivalence. With that I mean 2 Al3 plus can replace 2 Si4 plus only when 1 Ca2 plus is present. So, that is what the role of alumina. Now, coming back to the so called basicity of the slag. Now, basicity is another very important property. So, we can define either from ionic theory or from molecular theory. Now, from the ionic theory point of view, we can say that we know that most of the constituents are oxides in slag, some oxide donors, some oxide takers. So, when basic oxides are added, oxygen ions will be available, and these oxygen ions, they break the tetrahedron. So, any free oxygen ions available after satisfying the requirement of all acidic oxides, that is called the index of basicity. That means, the presence of free oxygen ions is an index of basicity of a particular slag. Now, with that I mean, for example, if I write SiO2, it will take 2 O2 minus ions to make SiO4 4 minus. Similarly, if I have a slag which has P2O5, that will take 3 O2 minus ions to give us 2 PO4 3 minus. So, if we now further add oxygen ions, then probably the oxygen ions will be free. Now, from where it will come? So, if I add calcium oxide, then it will give me Ca2 plus plus O2 minus. So, we can define now a neutral slag is one which contains enough O2 minus ions, so that each tetrahedron of acidic oxides is independent of each other. So, we can quantify the free oxygen which is available per 100 gram of the slag, that will be equal to NCaO plus an MgO plus an MnO plus an FeO, because they are all oxygen donors, minus 2n SiO2 because 2O2 minus is required, plus 3n P2O5 because 3O2 minus is required, plus NL2O3 plus so on. So, any oxygen ions which is available after satisfying the requirements of all acidic oxide, that will be free, and we can consider the free oxygen ions as the index of basicity of the slag. But well, from the shop floor point of view, it is very difficult to determine the free oxygen ions. So, normally the shop floor, the basicity is defined, say basicity is defined very simple way, weight percent of calcium oxide upon weight percent of SiO2. Now, suppose there are some other oxides are also present, for example, MgO is present or P2O5 is present, then basicity is defined in terms of CO equivalent of MgO. That means, MgO is not that effective as compared to calcium oxide. In that case, basicity will be defined, say weight percent CaO plus 2 by 3 weight percent MgO upon weight percent SiO2 plus weight percent P2O5. So, here what has been done, now suppose if the slag contains MgO also, then MgO is not that effective as calcium oxide, it is only 66% effective, hence that has been taken into account. They are simply the index of basicity. Now, we can also define a sort of a free calcium oxide. In literature sometimes you call excess base. I will call for example as a free calcium oxide. As we have seen in case of ionic nature of the slag, that free oxygen ions is the index of basicity, and that free oxygen ions can take part in the reaction. Similarly, free CaO is an index of basicity in the sense that that free CaO can take part in the reaction. Now, we define for example, say a basic slag is one which neutralizes all the acid components of the slag. Normally, in steel making we have for example, SiO2 and P2O5 are the acidic oxide. So, in order to define free CaO, for example, if I consider CaO SiO2 system, if I consider CaO SiO2 system, then free CaO will be available only when the requirement for SiO2 is completely met. With that I mean that when the compound 2-CaO SiO2 has been formed, then and then the excess CaO will be available. That means, that excess CaO now can take part in the reaction. So, if I want to define for example, in kg free CaO, that will be equal to kg CaO added minus say 112 upon 60 kg SiO2. Now, since 60 kg SiO2 needs 112 kg of calcium oxide, from there this equation comes. Now, for example, if I take 100 ton hot metal, say if I take 100 ton hot metal, 1% silicon, then silicon is equal to 1000 kg, SiO2 will be 2143 kg, and then the free CaO in kg, that will be equal to kg CaO minus 112 upon 60 into 2143. That what does it mean? That means that free CaO in slag will only be available when added amount of CaO is greater than 112 by 60 into 2143. Now, this comes say kg CaO minus approximately 4000 kg calcium oxide. So, only that CaO which comes after subtracting this amount is the free CO, and that can take part in the reaction, for example, for the removal of phosphorus. Now, if you also consider phosphorus into our discussion, then free CaO again in kg, that will be equal to kg CaO added minus 112 upon 60 into kg SiO2 minus, say, now we have say 142 kg P2O5, it needs 160 kg 68 kg of calcium oxide. We are considering the compound 3CaO P2O5. So, that will be minus 168 upon 142 P2O5 in kg. So, if I put it this way, this will be kg calcium oxide minus 1.86 kg SiO2 minus 1.183 kg P2O5. So, that is what the concept of free calcium oxide in the slag. You can also consider that free CO will, you can also call it to be the activity of calcium oxide in the slag. Now, this is what a very important thing to understand the concept of free CO in the slag. Now, here it should be noted that if P2O5 forms as a function of time, then accordingly the free calcium oxide in the slag will also vary. We have seen basicity, we have seen oxygen reduction potential of slag. Now, we have to consider the activity of slag. Now, say activity of slag component. Activity of slag component. Now, what activity means? Activity is the effective concentration. That particular oxide will be active or will be available for reaction when it is free in nature. So, that is what the most important. Now, from a steel making point of view, we are looking for example, activity of calcium oxide, because calcium oxide is a component which makes slag basic, which forms compounds with SiO2 and P2O5. So, it should remain free. Then we are also looking for activity of FeO, because activity of FeO determines oxidation and reduction potential of slag. The availability of oxygen from slag to metal, that will depend upon what is the activity of FeO, that is what is the free FeO content of the slag. Then we are also looking for activity of P2O5. Now, since activity of P2O5, we want that activity of P2O5 should be very, very low, because we want to remove phosphorus, phosphorus will form P2O5. So, if its activity of P2O5 in the slag is very high, the phosphorus will revert back to the metal, and that is what we do not want it. So, conceptually what we can say, that the activity of any component, it depends on its mole fraction and activity coefficient. Now, the slag, it follows Raoult's law, because their concentration is more than 1%. So, Raoult's law is obeyed, and according to Raoult's law, activity of any component, that is equal to activity coefficient into mole fraction of that component. Now, activity of FeO I have enough said when we are considering free CO. Then let us take it activity of FeO, which is a very important component for steel making. So, activity of FeO, that is equal to gamma FeO into NFeO. Now, log gamma FeO is equal to minus 0.7335 log NFeO minus 0.2889. Now, if I write for example gamma FeO, that will be equal to 0.514 NFeO to the power minus 0.7335, and if I write now activity of FeO, that means this is my equation number 1, this is my equation number 2. Now, if I combine equation 1 and 2, then I get activity of FeO, that is becomes equal to 0.514 NFeO to the power 0.2665. So, this equation one can calculate the activity of FeO. Now, for example, if I take V ratio, that is the basicity ratio, equal to 4, then I consider, say for example, I take NFeO, that is equal to 0.488, and I determine activity from here, then the activity of FeO, it comes equal to 0.424, and similarly if I take V is equal to, for example, 3, then NFeO, that is equal to 0.350, I determine gamma FeO, that comes equal to 1.110, then I calculate activity of FeO, that is equal to 0.388. I take another example, I take V is equal to, for example, 2.5, I calculate NFeO, that is equal to 0.273, then gamma FeO, that is equal to 1.332, and activity of FeO, that is equal to 0.363. Now, what this calculation means? Now, this calculation means that in a CaO SiO2 system, if basicity of the slag as defined by weight percent CaO upon weight percent SiO2, it increases, then gamma FeO decreases, and activity of FeO, it increases. As you see from here, that if the V ratio is 2.5 to 4, if you go is, then the gamma FeO, it at V is equal to 2.5 was 1.332, and at V is equal to 3, gamma FeO becomes 1.110, and for V is equal to 4, gamma FeO can be calculated to the value of 0.87. So, the gamma FeO decreases, and as a consequence of decrease in gamma FeO, activity of FeO increases. Now, so that is what the important consequence of this particular calculation, that increase in the V ratio, that is increase in the basicity, increases the activity of FeO, and that one can understand also. That means, if you consider CaO FeO SiO2 system, then in CaO FeO SiO2 system, as we increase the amount of calcium oxide, then the FeO becomes free, and hence its activity increases. So, it is logical also. Now, the next thing that I will come now, the important property is the slag foaming. Now, say what is a foam? What is a foam? Foam in fact is a dispersion of gas bubbles in liquid. A liquid is said to be foaming when gases could not escape through the liquid, and as a result the height of the liquid, it increases. Now, given this definition, now in steel making, slag foaming occurs due to the following reaction. In steel making, slag foaming occurs due to the following reaction. One reaction is FeO plus C, that is equal to Fe plus CO. Now, this reaction occurs within the slag phase, within the slag phase. Another reaction is carbon in metal plus oxygen in metal, that is equal to CO, gaseous phase, and this reaction occurs at gas metal interface. Now, when the CO bubble which is forming by this reaction or by this reaction, they are unable to escape through a layer of slag, then what will happen? The slag will foam, that is bubbles will be entrained, and the height of the slag will increase. So, the important point in case of foaming of the slag is that gas bubble should be entrapped, easy escape of CO bubble when it is not there, then slag is said to be foaming in nature. Now, the question is slag foaming desirable? Well, to some extent yes, because when the slag foams and if the droplets are entrained, then the interfacial area increases and the rate of reaction is also very fast. Now, in another advantages are also of the slag foaming, The first advantage is that the shielding of molten metal against reoxidation. Shielding of molten metal against reoxidation. Shielding of molten metal. Second, slag foaming also acts as a thermal barrier. Also acts as a thermal barrier. It shields the refractory lining. Shields the refractory lining, particularly in electric arc furnace steel making. Fourth, it controls heat transfer from post combustion flame to the metal bath. Now, how can slag foaming be quantified? Say quantification. Quantification, now for example, if you take a bath, here is a liquid, here is a liquid, and then if we allow the gas to flow, and this is now the liquid is here. So, these are the gas bubbles of different sizes, and this is again the slag layer. Because slag was so viscous that it did not allow the gas bubble to escape from the system, as a result slag has formed, and this particular thickness we call as a foam layer thickness. So, now we can define foaming index. We can define, for example, foaming index, that is equal to foam layer thickness, upon average gas velocity, average gas velocity. So, if this is in meter, this is in meter per second, then the foaming index comes in seconds. So, foaming index comes in second. Low foaming index means gas can escape easily, or residence time of the gas bubble in the slag is small, hence the slag will be of lower foaming index. Higher foaming index means the escaping of the bubbles is delayed, and hence slag will foam. So, again one can also say that the smaller size of the gas bubble cannot easily escape as compared to larger size of the bubble. That means, the gas bubble also play an important role, and in relation to steel making, when the gas bubbles they are formed at the slag metal interface, then do not have sufficient chance to grow, and such slag may foam much as compared to the reaction when C plus O occurs at the gas metal interface. Now, at the gas metal interface, the gas bubble has sufficient time to grow, they become bigger sizes, and they can easily escape through the slag. I mean, this is just a common sense here. So, now in this relation, what is a foam life? Foam life is directly proportional to foaming index. Low foaming index, low foaming life, higher foaming index, higher foaming life. Now, the parameters that control the foaming, there one is the, for example, slag properties, then bubble size, then the decarburization rate. Now, decarburization rate, higher or lower decarburization rate, because decarburization is the reaction which generates carbon monoxide, and then location of gas forming reaction. In fact, bubble size and location of gas forming reaction, they are little bit interrelated. That is, if the location of the gas forming reaction is at the slag metal interface, then, and if at the gas metal interface, as I explained, a lower decarburization rate and higher decarburization rate, more amount of carbon monoxide will be evolved, and if the slag is not sufficient viscous, then it will not allow CO to escape through the slag layer. Now, about the slag properties, I will summarize some of the slag properties. The effect of slag properties, the increase in viscosity increase in viscosity increases foaming index, increases foaming index. Then foaming index decreases with increase in basicity of slag, with increase in basicity. Foaming index decreases with CaF2 addition, calcium fluoride, because it decreases the viscosity of the slag. Now, foaming index increases with increase in volume concentration of particle, with increase in volume concentration of particle. Now, why it does so? Can you imagine? Because the more particles are there in the slag, the viscosity of the slag increases, and on account of which the foaming index increases. Now, the viscosity of a slag which is entrained by the solid particle, that is equal to mu, is equal to mu 0 1 minus power minus 2.5, where epsilon is the particle concentration, the volumetric particle concentration, mu naught is the viscosity in absence of particles, in absence of solid particles. So, foaming index can be quantified as follows. Say foaming index sigma 0, that is equal to 1.82 mu naught upon 0.5 diameter of the bubble raised to the power 0.9. Now, here mu naught is the viscosity of slag, I am writing once again, in the absence of solid particles. So, that is to be substituted in kilogram per meter second, then rho is the density of slag, it has to be substituted in kilogram per meter cube. This is the surface tension, and it has to be substituted in Newton per meter, then dB is the diameter of bubble, the dia of bubble. Now, if I want to know the foaming index in the presence of solid particles, then what I can do? I can substitute the value of mu 0 from this particular equation, and I get the foaming index in presence of solid particle. If I divide by foaming index in the absence of solid particle, that will simply come out to be 1 minus epsilon raised to the power minus 2.5. So, effectively what it says that the foaming index increases with increase in the volume concentration of solid particles. Now, this I can illustrate by a simple problem. Now, for example, let us calculate the foaming index. Let us calculate the foaming index of slag, which is 60% calcium oxide plus 35% Al2O3 plus 5% SiO2 at 1773 Kelvin. Now, this temperature in this calculation is not important because I am giving you the properties. So, this is in the absence of solid particle, the viscosity mu 0 is 3.5 kilogram per meter second, density 2500 kilogram per meter cube, surface tension 1.1 Newton per meter, and let us consider diameter of the bubble 0.005 meter as a typical example. Now, if I substitute all the values, then I get foaming index that comes to 14.3 seconds when diameter of the bubble is 0.005, when diameter of the bubble that is equal to 0.005 meter. Suppose I take now diameter of the bubble is 0.01 meter, rest all the properties of the same, then the foaming index in the absence of solid particle, it comes 7.67 seconds. Now, you see that is the increase in the diameter of the bubble, it decreases the foaming index. Now, if the slag contains for example 0.1 and 0.2 volume fraction of solid particles, then I can calculate sigma, that is equal to sigma 0 1 minus epsilon to the power minus 2.5, and that comes 18.6 second when diameter of the bubble, that is equal to 0.005 meter. Now, this has to be compared with 14.3 seconds. So, now increase in solid concentration, it increases the foaming index. Now, same thing I can illustrate for diameter of the bubble 0.01. So, this will come sigma, that is equal to sigma 0 1 minus epsilon to the power minus 2.5, and that will come 13.4 second for diameter of the bubble equal to 0.01 meter. So, what it illustrates? Increasing the diameter of the gas bubble, it decreases the foaming index. Increasing the volume concentration of particle, it increases the foaming index. So, that is what I have to say. So, here are the questions for self assessment. So, I have framed around 8 questions for you for self assessment. I just read very fast. So, what is the role of slag in steel making? How does the progressive addition of calcium oxide influence the structure of molten silica? What do you understand by the silica equivalence of slag of alumina? What is the significance of foaming index of a slag? We have already discussed. Discuss the properties of slag which influence the foaming of slag, that already I have listed. Why does addition of Na2O drastically reduce the viscosity of silica rich slag when compared with calcium oxide addition? This already I have explained, because Na2O is a single charge. Now, calculate the foaming index, though I calculated for you, you can again recalculate, and also you can procure the different slags and find out the different properties, and you can categorize the slag with reference to the foaming index. Last question is, based on the molecular nature of slag, calculate the minimum free CaO that is required, which contains SiO2 and P2O5. How much minimum free CaO would be required in a slag formed during refining of 100 tons of hot metal containing 1% silicon and 0.25% of phosphorus to steel containing 0.05% silicon and 0.02% phosphorus? Remember, you have to subtract that amount of silicon and phosphorus which is going to steel, rest will be captured by calcium oxide. So, good luck for solution of the problem. Now, the next slide, they are the reference for your further reading. There are few references are here.